Today we're going to get into some of the nitty-gritty using a one-shot instruction. With the RS Logic's Arena, if you're familiar with that, a one-shot instruction had its own unique memory location. So it was truly a read-write instruction. That type of one-shot instruction, not here, not in Micro 800, okay? That type had a memory location that when the rung went true, it looked to see if that memory location was on. If it wasn't, then it had a true out going on into the rung. If it was on, then that meant it had already been there and fired its one shot. It had had its one scan true. Okay, now with the one-shot instructions with the Micro 800, they're a little bit different. Instead of looking at a photo eye, then a one-shot instruction with its own unique memory location, then a true out on a one-shot, etc. With Micro 800, you use the photo eye memory location as a pulse rising or pulse falling. So it's a little less programmed. So it's actually more convenient in a way. So what we're doing in this lab project, today anyway, in our discussion, is we're going over the part of project M11 where we're comparing the coil types and we're trying to exhaust the different combinations. But we're also introducing the idea or the behavior and the sequence of events of instructions that come before the one shot and after the one shot. In other words, what order do they have to be true based on the scan in order for the rung to be true and do the execution of whatever the final instruction was. So this is really where it gets more interesting using the one shot. And I'll guarantee you, not only will you come across a lot of one shots in your career that you have to interpret, and I do show you how to capture, to set a bit trap to prove that it did actually one shot and go on. Not only will you run across a lot of them and probably need to use the bit trap, you're probably going to use them yourself because you'll sit and you'll have a challenge. You'll think, how in the world am I going to do this? I just only want this to happen once and not happen again. That's where the one shot comes in. These are the 7 rungs that you created for this next part of the project, Lab Project M13. The first 2 rungs we can pretty much ignore simply because, well, at least the first rung, true if on, energize output, or if you like, direct contact, direct coil. If this is true, then it turns on output 0, 0. If this is false, then it turns off output 0, 0. Everybody understands that. This one is just the opposite in that this is a reverse coil, which means if this is false, then this is on. If this is true, then this is off. So we have direct coil, reverse coil, we have set coil, we have pulse rising edge. It's a one-shot output type instruction, and then we take that single pulse and we capture it with a set instruction. So gotcha output 3, that just means if this gets set, then we know that that went on for one program scan. This is just the opposite, falling edge, and the gotcha output 4 proves that this did execute for one program scan. And then we have a single run here, so you can easily reset these because we expect you to exercise this logic on your own multiple times, observing each coil type until you're fairly comfortable with their functionality. So let's save and download this. First, we're going to turn on the simulator. We got to power it up. You can't download to a controller that's not powered up, so we power up the simulator and move it out of the way. Save and download. I did want to show you one thing that I don't have in the manual, and that is the warnings that come up. Now typically I don't go look at warnings, only errors. If it's not going to compile and download, then I go look to see what's wrong. In this case, I was curious, so I went to look at these 2 warnings. Basically what it is saying is run mode change not recommended with the P and N type coils because value depends on transition of rung equation. And we've kind of pointed this out before that depending on the state of the conditions. For instance here, if input 0, if that input is on and we download, this rung transition is going to pulse output 3 even though you may not have purposed for that to happen. We mentioned that earlier in a discussion, so I wanted to point out these warnings and what they mean. If you don't like the warning, in other words, if you want to eliminate all possibilities, well, first thing I suggest is don't use the P and N type coils. They're not necessary. In the older programming of ladder logic diagrams for Rockwell, RS Logics, etc., you could do anything you needed to do with a single one-shot instruction. There was a way to write the code to get the exact same outcome that you get here with these different instructions. So you use the P and the N at your own risk in a sense. If we want to be able to see all of these rungs simultaneously, then I'm going to have to downsize the logic. So I dropped it down one level. Unfortunately, that means that on your screen you may not be able to read all of the text. So I'm going to bump it back up because we're going to look at 1 or 2 rungs at a time, not all 7 rungs plus the reset rung. We don't even care about the reset rung as far as seeing it. It's just a function so you can reset some of these set bits. So I'm going to make this a little larger and we'll go from there. So the first one, the first rung, that's the rung everybody is familiar with. The second one's a little different. That's the indirect coil, reverse coil, I should say. And if input 0 is off, then the false execution for that instruction, the reverse coil, does the reverse of the direct. So if true makes the rung 1 there, if a true rung turns on output 0, then the reverse would be a false rung would turn on output 0, except we're not using the same outputs. We're using different outputs, so there's no conflict here. So you can see right now, and I'm going to toggle on 0, so just watch the first 2. See, it reversed. So you could say that this coil right here, the reverse coil, is the reverse in behavior of this coil. True in turns output 0 on, false in turns output 0 off. This is just the opposite. True in turns it off, and false in turns it on. Enough said about that. Now the set instruction, which we're already familiar with, it's a true execution only. So it's just like the direct coil, except it only has a true execution. The rung is false right now. We're talking rung 3, but the bit is on. If I reset it, and I can do that by toggling 1, and that's the last rung down there at the bottom of this that resets those bits. You understand how this instruction works. It has a true only execution. When it's true, it turns on output whatever memory location it's addressing, and when it's false, it does nothing. There's just nothing. This instruction, which is the rising edge or leading edge one-shot coil. So when I turn on input 0, this is going to go on for one program scan. And to prove that it went on, we, in the very next rung, we're reading that bit and setting a bit just to prove that it was actually executed. So I'm going to input 0 on, then off, and you can see that output 3, you didn't see it go on, and here it shows this is false, but it's set, which means it did execute the true execution for one program scan. So for one program scan, it says, hey, OUT03 in memory. And remember, these instructions have no idea that output 3 over here by way of your buffered outputs, see, notice that output 1 and 2, they're turning on real outputs 1 and 2 down here on your simulator. So these instructions have no idea what those bits in memory are doing. It's just turning on bits in memory. Okay, we'll reset that again. Now this one's going to stay on. Output 1 is going to stay on as long as this rung is false. Then we have this falling or trailing edge one shot. And if I turn on input 0, now watch output 4 there, 6th rung, nothing happens. And we know output 4 didn't go on because in this rung down here, the one below it is the capture rung. If this had gone on, it would have set that bit. Now I'm going to turn it off. And so what you're going to see is when the rung goes false, it's going to do a true execution on this and set output 4 equal to 1. And then on the very next scan, it flips it back. So you're not going to see output 4 do anything. But down here, you'll see that we captured that. So I'm going to go off. So watch rungs 6 and 7, mostly 7. Okay, see 7, rung 7's false, but gotcha output 4 is set on. And that's really all there is to this part of the lab. Now notice there's no black rungs. The rungs and the color have to do with the state of the conditions and permissives, or the read type instructions, statement type instructions in the rung. So if you had a one-shot instruction over here in the conditions, then the rung would be black, because it's neither true nor false in a sense. So let's save that. Well, let's answer the questions. And I'm going to go back and turn off everything. I could right click. You can do that. You can right click these things and toggle the bits. See, they didn't get rid of this one because that's on because this rung is false. Remember, this is a reverse coil. So if we go down here to the last rung, you can see gotcha 4 is still on. I'll toggle that off. I could have just toggled input 1, but I like to kind of mix it up a little bit. So let's go back to the at-rest condition, and you had a little box of questions in the manual. Input 0 is off. Input 0 was on or off. Well, it was off. Input 0 is off. Input 0 was off. Output 0 is off. Output 1 is on. Output 1 was on. Output 2 is off. Output 2 was off. Output 3 is off, and it was off. Output 4 is off, and it was off. Now remember that these questions don't make a lot of sense on the very first step, simply because we haven't made any changes. We have not changed the state of any bits in memory, so we're not really seeing any action here to make the term was for past tense relevant, because that's what one-shots are all about, the difference between was, is, and what is. And you have 3 different phases there, basically. You have before you triggered the one-shot, you have one program scan while it's triggered, so to speak, and then you have after the first scan when it goes back to the other state. So there's 3 elements there in the timing: before, during, and after. Why is output 1 on? Output 1 is on because it's a reverse coil. Flip input 0 to the on position and leave it on. So we go over here and we flip on input 0. And now we look and we see that input 0 is on. It was off. Output 0 is on. It was off. Output 1 is off, and it was on. Remember, reverse coil. Output 2 is on. Output 2 was off. Output 3 is off, and it was off. Gotcha output 3 is on, but it was off. Output 4 is off, and it was off. Gotcha output 4 is off, and it was off. Why is output 1 off? Well, output 1 is the reverse coil, and the true execution for that is to turn off output 1. So that's why output 1 is off. Next, press and release input 1, and then flip input 0 to the opposition and leave it. So let's do it in that order as it said in the manual. What we just did was we exposed these rungs to input 0 going off, that momentary instantaneous state of going from input 0 true if on, going from true to false. That was the goal for this next step. So looking at the logic, input 0 is off, input 0 was on, output 0 is off, but it was on, output 1 is on, it was off. Remember, this is a reverse coil. Output 2 is on, and it was off. Well, remember, output 2 is controlled. It's a set instruction controlled by input 0. Right now it's on, and before, I guess you could have answered that either way, depending on how many steps you wanted to go back, because we just turned it off. So we could say it was on. Output 3 is off, and it was off. Or if you want to take the last step, In other words, it was off when input 0 was on after one scan. In other words, for one scan, output 3 would have gone on, but it would have went right back off a long time ago. So let's just say that it was off. Gotcha output 3 is off, and it was off during this last step. Output 4 is off, and it was on, and the reason we know it was on is because in the next question, gotcha out 4 is on, but it was off. So reading these out loud is really confusing. You're writing down your answers here because you're thinking about each individual rung and each coil type. So I'm just going through the answers so you've got some way of checking what you wrote down in your manual. Compare the above screen capture to the previous. What differences do you see? Well, you could elaborate quite a bit on that. Basically, you see the difference between a false to true transition and a true to false transition. That's basically the difference that you see. We have the instructions coils P and N. Those are the ones that we're really focused on. We're not focused on set and reset or even the reverse coil. The reverse coil is kind of new. We haven't really used it. The reverse coil is a no-brainer. It just does the reverse of what the direct does. Okay, so save and disconnect. In our new logic, we have 4 pairs of rungs. Rung 1 and 2 represent one demonstration, 3 and 4, another one, 5 and 6, and then 7 and 8. So in the first pair, we are considering the rising edge or leading edge, if you like, going from false to true, true-if-on instruction, and we're using a set bit to capture that it did occur. In the second pair, we're kind of flipping it around and we're using a true-if-on but with a rising edge coil instead of a rising edge true-if-on. And then in the third set, we're using a falling edge true-if-on to energize an output, and then we're capturing that it did occur with the second rung of the pair. And then in the last pair, we're using a true-if-on to execute a falling edge coil, and then we're capturing it with a set instruction. So we're comparing using one-shot read instructions with one-shot write instructions so you can have a good comparison. Now remember, in the old days, or not really in the old days, but in other software packages for other Allen Bradley products, you can accomplish the same thing by combining instructions. My personal preference would be the least different instructions that you use, the better. In other words, if you can write your program with, let's say, 8 different instructions instead of a dozen, I think it makes it easier to read, even though you do have some combination instructions to get the same function. The vote's still out on that. So let's save this, download, and go online. Our simulator is running. We go over here and look. It's not faulted. That's a good thing. So we'll save and download. And of course, we get the same warnings. Remember that I did mention earlier that when you use a rising edge or falling edge contact, depending on the state of the bit, when you go to the run mode, whether it's from powered down and booting up or run mode change, you risk the logic executing when there really was not a change in state of that bit memory. It's only that you did a mode change. So that's why I'm in favor of using less instructions and being more deterministic in how you do this. But I'm just showing you the instructions straight up here. Let's execute the first one. So what we're going to do is we're going to compare using a rising edge contact to a rising edge coil. And to do that, we're going to turn on input 0, so watch the first 4 rungs, turn them on, and then back off. Notice that we got the identical result, that rung 1, this instruction turned on output 0 for one program scan. In rung 3, this rising edge coil turned on output 1 for one program scan. And the reason that we know this is because of our gotcha output 0 and gotcha output 1. In other words, we were able to capture that these two give you the same result. So it's up to you which one you like the best. What I had you do in the manual was, and I will reset this and do it again. I had you turn on input 0 and leave it on. Input 0 is, I had you flip on input 0, and notice we have a black rung here and a black rung down here. That's because we have true-if-on instructions that are one-shots. So I turned on input 0, and you're looking and saying, well, it looks like it's on here but not here. Well, remember, you're looking at the text. The text is red, the text is red. The difference is that this is only true for one scan, and this is true continuously as long as it reads input 0 as being on. So your answers, input 0 is on, input 0 is off. This is in your box of questions. Output 0 is off, but it was on for one scan. Gotcha, output 0 is on, it was off. Output 1 is off, but it was on for one scan. Gotcha, output 1 is on. Gotcha, output 1 was off. It was off before we turned it on. Now let's look at the second group of 4 rungs. We have pairs of rungs, and we're comparing coil types, but we're really comparing them in 2 groups of 2. So we scroll down so we can see 5, 6, and 7, and we're going to do the same thing. So let's do the same thing. Well, first we'll reset. Now you could right click on these and then toggle, or you can just use what we had before and you go on and off with 1. It says reset the gotcha bits and then flip input 0 to the off position, leave it off. Well, I already flipped it off, so I'm going to flip it back on, and then I'm going to reset the gotchas. Now let's look at these. Remember, we're comparing gotcha 2 with gotcha 3. If they behave identical in results, then rung 5 and rung 7 are equivalent in functionality. So watch rungs 5, 6, 7, and 8, in particular 6 and 8, when we turn this off. Notice that both gotcha output 2 and gotcha output 3 are the same, which means that both of these rungs had the same effect on the bit and memory that they were addressing with the coil, whether using a falling edge on a direct coil or a true-if-on on a falling edge coil. They behave both the same. And the questions in the manual, input 0 is on or off. Right now, input 0 is off. It was on. Output 2 is off, but it was on for one program scan. Gotcha, output 2 is on, but it was off before we executed the logic. Output 3 is off, but it was on for one program scan. Gotcha, output 3 is on, but it was off before we executed the logic. Okay, so that wraps up the comparison of these coil types in the sense that we were comparing them to the contact types of the same similarity. Save and go offline. This is our next chunk of logic. This is our next piece of code, and really rung 1 is the crux of our focus here. Rung 1 is the rung that we actually want to look at. In parallel with output 0, we have output 1 with a set instruction. As per usual, we're doing this to capture the fact that output 0 was pulsed for one program scan. However, I've added to this. In the second rung, I have another reset for the following third rung. The third rung, I am equating it with the first rung. So I'm going to drag this up here so they're right next to each other. In this rung, it says if input 0 is on, and if this is the first scan that input 0 is on, and if input 3 is on, then energize this bit, direct coil, set this to 1. Then on the very next scan, if this is still true, then this is now false out, and it doesn't matter whether this is true or not, false in, false out, and the false execution sets output 0 back to 0, back to off. And again, this set instruction, output 1, guarantees that we will be able to see that it did go on. The point that I'm making in this logic is if this goes true, this instruction, this rising edge, true-if-on, if it goes true and this is not true, then that one shot is wasted. In other words, this was true out, but because this is false, it's false out because these are ANDed together. We have to have all three of these true on one scan. There is a difference though between the order in which these have to be true. If we flip these around, the logic may not behave the same. It depends on what's controlling input 0 and input 3. Now this might be a photo eye. We're treating it like a push button by just toggling it over here on the simulator, but it could be a photo eye. So let's say this is a photo eye and there's no package on the conveyor blocking the photo eye, so input 3 is off. Along comes another situation blocking another photo eye. This goes true, that goes true, but because this is false, whatever output 0 would be doing doesn't happen. And then as long as input 0 stays on and this stays true, this stays false. So if this stays true and this goes false on the next scan and then this goes true, it's too late. Input 3 has to be on, or we'll just say this instruction has to be true on the same scan or earlier than this being true. One scan late, you're not going to turn on output 0. They could both be true on the same scan. That's probably unlikely, but it's not impossible. Remember, these are all three inputs, input 0, 1, and 3. They could be push buttons, photo eyes, proximity switches, you name it. So we have a condition that has to be true in order to one-shot, and this one-shot is true if input 0, 1 is on. So input 0, 0, 1, and 0, 3 all have to be on, but they have to be on in a specific order, in that if all three of them are on at the exact same instant, in other words, on the last scan, all these inputs were off, and then on this scan, they're all on, then you're going to one-shot output 0. If input 3 is on and you turn input 0 on, if input 1 is not on, it's not going to be true out. So you have a specific sequence here that has to be met. So let's say this, oh, by the way, and then down here, this input 1 true if on, input 1 right here, and this together, these two, this is actually an instruction, this is a function. It doesn't have an address. What it does internally, it's rtrigger 1. If you add another one of these, it's going to be rtrigger 2, and you could name it if you wanted to. You could call it input 0, 1, one shot. As a matter of fact, we'll do that. Just for grins, we'll go to block selector, and we'll go down here, and we'll call it input 0, 1, one shot. I didn't want an exclamation there. Input 0, 1, one shot. So this, if you want to call it an instruction or function, along with this instruction, give you the same result as this one single instruction up here. If when input 1 goes on, this one shots it to this instruction. So for one program scan, you have a rung true out. If this is true, then we fire output 2, otherwise we don't. So let's save this, download, and go online. So save, download. You see the infamous black image right here. That means it's neither true nor false. It actually is false out right now, but it's not shown as blue because it's based on a one-shot function, not on a standard true if on instruction. So in the manual, I have you turn on input 0, then turn on input 1. Of course, nothing's going to happen because input 3 is off, so this is false and it goes no further. And I have you look closely at the two images in the manual. What difference do you see? Well, the difference that you see is input 0, 1 is on, and that's all that you see. So if you were looking at this in logic and didn't have this set instruction here going to output 1 to tell you whether or not it actually went true, you wouldn't know if this ever went true. Let me show you what I mean. I'm going to turn on input 3 and then off again. See, I turned on input 3. Now, there's no way to tell the difference between this and this when it comes to looking at this, because notice that this does not change. Let's go back and do this again. Input 3. Notice this does not set. So if you were looking at this in your code, you were troubleshooting on a machine out on the shop floor, and you looked at this, you would not know whether this wrong ever went true or not, because this is never going to show on, because it's only on for one program scan. You can't see it, the screen can't show it. So the only way that you can know that this ever was true out to output 0 is if you have a bit trap. That is one of the difficulties of troubleshooting logic that has one-shot type instructions in it. But you can always add a bit trap. And remember, you don't have to put in the reset. We have a reset down here just to make it more convenient for you, but we can just toggle it. So if I was going to troubleshoot, I would put that in there, and then I would reset. We'll turn off 3, and we'll turn off 1, and we'll leave 0 on. Okay? Now, let me do this. Watch this. I'm going to turn on input 3, and then I'm going to turn on input 1. So input 1, remember, it's a combination of this instruction and this instruction. So input 1 was off, and then when it went on, because input 3 was on, in other words, when this was true out, this was already true. So you got a true out all the way through. It pulsed output 0, and it set output 1. And primarily what you want to notice is that this logic down here, in other words, watching output 0 and 2, they behave the same. You don't see anything. But it's output 1 and output 3 that you're interested in because they behave the same. Okay, I'll reset with 4. Now, nothing's going to happen because and this really is a better picture. See, this is false out from this function. So if I turn off input 1, now watch when I turn it back on. See, it turns back on output 1 and output 3. So if you're trying to understand this instruction, remember it's the same as a true if on and a rising trigger. In the manual it said, why will you never see the instruction addressing input 0, 1 go red true, even though you know that this instruction had to be true when you flip the switch on? Because it's a one-shot. In the next set of questions, look closely at the 2 images above. What difference do you see? And what we see here is that input 0 and 3 are on, but input 1 is not. In the first image on the left, all 3 inputs are on. That's a question mark. That's true. Are either output 0 or output 1 in the on state? No. If all 3 inputs are on and the logic is ANDed in series, why are the outputs not on? Straight up, when the first 2 go true, if the third one, which is true if on input 3, if that's not true, then your one shot happened in the darkness. Never made it to the end of the rung. Watch very closely in this next step. Flip input 1 to the on state and leave it on. So it is on here on the screen. Are all 3 inputs on? Yes. Are all 3 instructions true? No. Are both outputs on? No. Was the rung true when you flipped input 1 to the on state? Yes. Why is it not true in the above image? Because it's a one shot. It was only true for one scan. You can't show that. So rather than have it be red, blue, or anything else, they just show it black because they can't show it on the screen. Here they can show off and on. Here they can show true or false. Here's false down here. But these instructions and the state of the rung they can't show because it was momentary. Flip the reset switch, input 4 to the on state, and leave it on. So we're going to flip on the reset, and of course that's going to force output 1 and 3 to be off at the end of the program scan no matter what happens in rungs 1 and 2. Is input 0 on or off? It's on. Input 1, is it on or off? It's on. Input 3, is it on or off? It's on. Output 0, is it on or off? It's off. Output 1 is off. Which rungs are true? The last rung. That's the only rung that's true. Which rungs are false? Rungs 1 and 3. Now, keep in mind that in your manual you don't have rung 2. So really, it should be, the first rung is false, and the second rung, which is the third in the image you see here, is true. And it keeps executing the reset. So it wouldn't matter what the first rung did or the second rung. The third rung, last man wins, is going to reset that back to 0. Now these instructions are the most powerful instructions at the bit level because they can detect sequence of state changes. In other words, if you want to detect a certain sequence, then you would put the primary or the first order where input 3 is, true if on input 3. In other words, that has to be met first. Then you could have the true if on for input 0 and then for input 1. But the IN3, that instruction, true if on, it's the preliminary that has to be there before the others are executed. So you can kind of catch the leading edge of something that has a prerequisite, and that is input 3 being on. I hope you found that interesting. If if at this point that you feel confused about the one-shot instructions, you need to repeat these lab projects over and over again until you have some level of comfort. I would not go on to the next one, which is going to be a practical example of a one-shot. Well, maybe that would be good. Go on to the next one and see if that clears it up for you. Sometimes a practical example solidifies the whole concept to you. So we're done today with this lab project. We'll see you for the next one.